Section 9.4 is on phasors for circuits. So let's look at a resistor. Good old Ohm's law, which we started with at the beginning of the semester, V equals IR. So here's the classic vision of V equals IR that we're used to. So if we want to write this in phasor notation, then it's just V, and make sure it shows up here, equal IR, where V and I are phasors. That's all we got to do. So it looks exactly the same. Looking at our inductor, V equals L di dt. So now in phasor notation, we get V vector equals J omega L I. So again, V and I are our phasors. And for our capacitor, we have I equals C dV dt. So this will give us I equals, I didn't want to write the C yet. I want to write, oh, that's very messy. Let's try a different towel here. There we go, close enough. I equals J omega C V, but we really want to write it in terms of V equals something to match the other ones. So if we rearrange that, V equals 1 over J omega C times I. So we can write it that way. We can also write this as minus J over omega C I, because 1 over J is equal to minus J. They're the same thing. So that's pretty much all that's in this, this section. So we're going to look at a couple example problems and work through those. V of t is given as 100 cosine of 60t plus 20 degrees volts. It's applied to a parallel combination of a 40K resistor and a 50 microfarad capacitor, and we're asked to find our I of R and our IC. Okay, so what can we do first? Well, let's go ahead and write our voltage V in terms of a phasor. So our voltage V is 100 at an angle of 20 degrees. We know V equals IR for our resistor. Right, so we want to use this. So we have V equals I, that's what we're looking for, times R. R is 40K. So we have this. But 40K is essentially 40K at an angle of 0. So we move this to that side, and we get, in phasor notation, I equals 2.5 at an angle of 20 degrees milliamps. We were asked to find lowercase I, meaning they want the I of t. So IR of t is equal to 2.5 cosine. Omega t stays the same, so we have to look up here. There's our omega t. So 60t plus our angle, 20 degrees milliamps. So there's our answer for IR. Now we want to do something similar for our capacitor. So we know the voltage across our capacitor because it told us these were in parallel. So we know our V. We're looking for our I. So I have IC is equal to J omega C times V, or IC is equal to J times omega, again that's 60, times the capacitor, 50 micro, times the V, 100 angle of 20 degrees. So I don't know that I wrote this out. I think I just put this one in my calculator as it is. And you get an IC that's equal to minus. Is it minus? It's a plus. Plus 300. No, that's not right either. Okay, well I don't have the answer on here. But anyway, you would get the answer there and then translate it like we did on this one. I don't know what this gibberish is at the bottom of the page. It's nothing useful. Okay, let's look at 9.31. We have a series RLC with an R of 80 ohms, an inductor of 240 milliamps, capacitor of 5 millifarads, and a V of T of this. So you don't need to draw it, but if you wanted to, you know, it's just saying everything's in series, so it doesn't matter what order, blah, 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 blah. There we go, we have that. Wants us to find I. Everything's in series, the same I is going through all of them. So there you go. So we want to represent all of these in our phasor notation. So R in phasor notation is just R. It's 80. L, how do we represent our L? Well, it's like this. This kind of starts to introduce us to impedance, which is in the next section. So we can write our L as J omega L. J times omega's right here. 2 times our L, 240 milli, or L is J 0.48, and it's actually in ohms, right? Because I have V equals I times something. That something is ohms. We know that because we know voltage over amps is ohms. So this is in ohms. Again, that's jumping a little bit ahead to the next section. Capacitance is minus J over omega C. So minus J over 2 times 5 milli, or minus J 100 ohms. So I have all of those in series, right? My R, my L, and my C are all in series. So I can come up with an equivalence, Z equivalent, an equivalent impedance. That's 80 plus J 0.48 plus minus J 100. They're in series, I just add them up. So I get 80 minus J 99.52 is my Z. If I want to write that in phasor form, I have the square root of 80 squared plus 99.52 squared. It's negative, but who cares because we're squaring it. At an angle tangent to the minus 1 of y over x. So you put that in your calculator. You get 127.69 at an angle of minus 51.21 degrees. So that is just our RLC. We're still looking for that I. V equals IR. So I equals V over R, where our R is the Z equivalent, right? So it's an equivalent impedance. V, right here, is going to be 10 at an angle of 0. Z is right above here, 127.69 at an angle minus 51.21. 10 over that 127.69 will give me 78.3 milli at an angle of 0 minus negative 51.21, so positive 51.21 degrees milliamps. So there's my I. Again, they asked for the lowercase I, meaning they want I of t. So we translate that back into a sinusoid. I of t is 78.3 cosine omega t. Gotta look up back at the original, was 2. So 2t plus the angle, 51.21 degrees milliamps.